Good afternoon, everybody. ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಇಂದಿನ ವಿಜ್ಞಾನ ಪ್ರತಿಭಾಶೋಧನೆ ಯೋಜನೆಯ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಡಾಕ್ಟರ್ ಬಿ.ಎಂ. ಚಂದ್ರಶೇಖರ್ ಅವರು ಹೈಡ್ರೋಕಾರ್ಬನ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಅವರನ್ನು ಸ್ವಾಗತಿಸುತ್ತಾ, ವೆಲ್ಕಮ್ ಟು ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಅಧ್ಯಕ್ಷರಾದಂತಹ ಪ್ರೊಫೆಸರ್ ಅಯ್ಯಪ್ಪನ್ ಸರ್ ಅವರನ್ನು ಕೂಡ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸುತ್ತಾ, ಹಾಗೂ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಆಯೋಜಿಸಿ ನಮಗೆ ದಿನನಿತ್ಯವೂ ಸಲಹೆ ಸೂಚನೆಗಳು ನೀಡುತ್ತಾ ಬಂದಿರುವ ನಮ್ಮ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಾಹಕ ಅಧಿಕಾರಿಗಳಾದಂತಹ ಡಾಕ್ಟರ್ ರಮೇಶ್ ಸರ್ ಕೂಡ ಸ್ವಾಗತವನ್ನು ಬಯಸುತ್ತಾ, ಹಾಗೂ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಾಜರಾಗಿರುವ ನನ್ನೆಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೂ, ನನ್ನ ಸಹೋದ್ಯೋಗಿ ಮಿತ್ರರು ಹಾಗೂ ವಿವೇಕ್ ಸಹೋದರರಿಗೂ ಕೂಡ ಸ್ವಾಗತವನ್ನು ಬಯಸುತ್ತಾ, ಈಗಾಗಲೇ ಹಲವಾರು ತರಗತಿಗಳಲ್ಲಿ ಉಪನ್ಯಾಸವನ್ನು ನೀಡಿರುವ ನಮ್ಮ ಚಂದ್ರಶೇಖರ್ ಅವರ ಬಗ್ಗೆ ಆಲ್ರೆಡಿ ಕಿರು ಪರಿಚಯ ಮಾಡಿಕೊಟ್ಟಿರುವುದರಿಂದ, ಹಾಗೂ ಸಮಯ ಅವಕಾಶವೂ ಕೂಡ ಕಡಿಮೆ ಇರೋದ್ರಿಂದ ನೇರವಾಗಿ ಚಂದ್ರಶೇಖರ್ ಸರ್, ಓವರ್ ಟು ಯು ಸರ್.
Thank you, Siddhagowda sir. Good afternoon, students. Welcome to the KPA Talent Search Program webinar series. In this particular talk, I will be discussing about hydrocarbons, and this particular talk will be useful for the students who are studying in +1, +2 level, and those students who are aiming at various competitive examinations like KCET or other competitive examinations, NEET examination and other competitive examinations. In this particular topic, here we'll mainly discuss about hydrocarbons. And hydrocarbons, you all know, they are the organic compounds which are made of hydrogen and carbon. See, these compounds, they contain only carbon and hydrogen. They are made of only carbon and hydrogen. But among hydrocarbons, there are different types of compounds. The four different types of hydrocarbons are shown here: alkanes, alkenes, alkynes, and aromatic hydrocarbons. So even though all these hydrocarbons, they are made of only carbon and hydrogen, they exhibit altogether different types of chemical properties. They show different type of chemical reactions. Even though they are made of only carbon and hydrogen, the question here is why they exhibit different type of chemical reactions. So the chemical reactions exhibited by these compounds are different, mainly because of the difference in the structural features of these compounds. Therefore, in this particular talk, I will be concentrating mainly on the structural features of these compounds, how the structural features of these compounds influence the chemical properties, how they influence various chemical reactions exhibited by these compounds. Because students, when they are studying organic chemistry, they study various varieties of different reaction of each and every class of organic compounds. And finally, they will be having confusion regarding the chemical reactions of each and every class of the compound. But if they study the chemical reactions based upon the structural features of those compounds, then it will be very easy to correlate, and it will be very easy for them to remember the chemical reactions. Therefore, here we'll discuss about the structural features of each and every class of these compounds, and how these structural features can influence the chemical reactions of these compounds. Let us take these compounds one by one. The first compound is hydrocarbons. There is some technical problem.
ಚಂದ್ರು, ಚೇಂಜ್ ಆಯ್ತೈತೆ.
Slide flow. Okay.
ಚೇಂಜ್ ಆಗ್ತೈತೆ, ಏನ್ ತೊಂದರೆ ಇಲ್ಲ.
ಚೇಂಜ್ ಆಗ್ತಿದೆಯಾ? ಸರಿ.
ಎಸ್.
Okay. Let us start with the alkanes. Alkanes, you all know, they are the saturated hydrocarbons. In alkanes, we find only two types of chemical bonds here: carbon-carbon single bond and carbon-hydrogen bond. See what the structure you are observing here. It is the structure of the simple alkane, the first alkane, the alkane containing only one carbon atom, that is methane. Methane, the molecular formula is CH4, and in the methane, there are 4 carbon hydrogen bond. You can see the structure of the methane. It has a tetrahedral structure where all the carbon hydrogen bonds are the sigma bonds, single bonds. Similarly, in the higher alkanes, for example, if you take the alkane with 2 carbon atoms, ethane, propane, or butane, in all those alkanes, the general formula of the alkane is CnH2n plus 2. And in all these alkanes, the only two type of bonds what we see here is the carbon hydrogen bond and the carbon carbon bond. And all these bonds are purely covalent bonds. And here in the carbon carbon bond, electronegativity of both the carbon atoms is very similar. In the carbon hydrogen bond also, the electronegativity of carbon is very similar to that of hydrogen. Therefore, these bonds what we see in alkane, these bonds are completely non-polar in nature. Therefore, these alkanes are completely non-polar molecules. And in the non-polar molecules like alkane, the main intermolecular force of attraction that exists between different molecules, it is only the weak van der Waals force of attraction. And this weak van der Waals force of attraction, the magnitude of this weak van der Waals force of attraction, it increases with increase in the molecular weight of the organic molecule. And because with increase in the molecular weight of the organic molecule, there is increase in the surface area of the molecule. As the surface area of the molecule increases, the contact between different molecules increases. And this contact, it increases the intermolecular force of attraction, and the intermolecular force of attraction, it increases with increase in the molecular weight of the compound. Therefore, the various properties which are exhibited by these alkanes, it is because of the nature of the bonding which is present here, and also the nature of the intermolecular force of attraction that is present between different molecules. Say physical properties like the variation of the boiling point, variation of the melting point, and solubility of these compounds can be explained considering these two natures of the alkane molecules. One is their non-polarity, and other one is the intermolecular force of attraction, that is the weak van der Waals force of attraction. Whereas the chemical properties exhibited by alkane molecules, they can be related to the nature of the bonding between carbon-carbon and carbon-hydrogen bond. Here carbon-carbon, carbon-hydrogen, both are sigma bonds and both are covalent bonds and both are almost completely non-polar in nature. You all know the bond energy of the covalent bond is very, very high, and it's very difficult to break the covalent bond. And difficulty is even higher where the covalent nature of the bond is higher. Therefore, the breaking of the carbon-carbon bond or carbon-nitrogen bond in the alkanes is very, very difficult. Therefore, whatever the reactions are exhibited by these compounds, all these reactions are the reactions which are very difficult to carry out in chemistry laboratory. And all these reactions are they occur only at very high temperature. All these reactions are high temperature reactions. Therefore, alkane molecules, saturated hydrocarbons, they are relatively exhibit very, very less reactivity, when compared to the alkene, alkyne, and aromatic hydrocarbons. Therefore, you will know when we discuss the alkene, alkyne, and aromatic hydrocarbons, you will know why the reactivity of those compounds is higher when compared to the reactivity of the alkanes. This variation of the reactivity, it is mainly because of the nature of bonding which is there in the alkane molecules. Let us see the variation of these properties in the alkanes with respect to their structures. So the first physical property, boiling point. If you take hydrocarbons, saturated hydrocarbons, alkanes, the first four members of the alkanes with containing carbon number 1 to carbon number 4, methane, ethane, propane, and butane. All these four are gases. And when the number of carbon atom increases, there is increase in the molecular weight of the compound. And as I said just now, as the molecular weight of the compound increases, there is increase in the surface area and the contact between different molecules. This increases the magnitude of the van der Waals force of attraction. Therefore, the hydrocarbons containing carbon number 5 to 17, carbon number 5 to 17, they are the liquid compounds because in those hydrocarbons, the molecular weight is higher, the intermolecular force of attraction is higher, and therefore the molecules that they get transferred from the gaseous state to the liquid state. And the viscosity of those liquid molecules, it further increases with increase in the molecular weight of the compound. Until up to around carbon number 17, whatever the hydrocarbons we have, all those hydrocarbons, they are liquid hydrocarbons. Liquid hydrocarbons. See, whatever the petrol we use, diesel we use, furnace oil, almost all those compounds, they come in this particular category. And all those compounds are the liquid hydrocarbons. And when the number of carbon atoms, it is more than 17, then the hydrocarbons, they become solid compounds, waxy type solid compounds. And waxy type solid compounds, there the intermolecular force of attraction is even high. Therefore, different molecules are tightly closely packed with respect to each other, and therefore they exhibit even higher boiling point. Therefore, boiling point of hydrocarbons, mainly alkanes, it increases with increase in the molecular weight. This is mainly because of the increase in the magnitude of the van der Waals force of attraction. Similarly, the melting point also increases with increase in the carbon content, with increase in the molecular weight. This is again because of the increase in the intermolecular force of attraction between different molecules. And here in the variation of melting point, we observe one more effect here, alternation effect. The hydrocarbons containing even number of carbon atoms, they exhibit higher melting point when compared to the hydrocarbons containing odd number of carbon atoms. And this is because this effect we observe only in case of the variation of the melting point. It is not observed in case of the variation of the boiling point. And this is because in the crystal lattice, when we observe the melting point, variation of the melting point in the crystal lattice, the hydrocarbons which are containing even number of carbon atoms, they can be closely packed in the crystal lattice when compared to the hydrocarbons which are containing odd number of carbon atoms. Even though, therefore, here, even though the number of carbon atoms, it is slightly varying, we observe large variation in the melting point from the hydrocarbons which are containing even number of carbon atoms to odd number of carbon atoms. Then solubility of these hydrocarbons, it is related to the nature of the bonding. Here the carbon-hydrogen bond, carbon-carbon bond, both are nonpolar bonds and like dissolves like. That means the nonpolar compounds, they are soluble in nonpolar solvents. Polar compounds, they are soluble in polar solvents. And since these compounds are nonpolar in nature, they are readily soluble in nonpolar organic solvents like carbon tetrachloride, chloroform, benzene. In this type of nonpolar compounds, these nonpolar hydrocarbon molecules are soluble. Whereas the polar compounds, like for example, sodium chloride, it is a polar compound. Water is a polar solvent. Sodium chloride is easily soluble in water, whereas same sodium chloride, if you put it in benzene, it is insoluble. It is insoluble. Whereas hydrocarbon, if you take, for example, if you take hexane and if you put it in benzene, it is easily soluble, because solubility here, it depends upon polarity. Non-polar compounds, they are easily soluble in non-polar solvents, whereas polar compounds are easily soluble in the polar solvents. These are three physical properties of the exhibited by the hydrocarbons, and the variation of these physical properties and the nature of these physical properties can be easily understood by considering the chemical structure of the hydrocarbons, and as well as the intermolecular force of attraction present between different molecules. Now let us come to the chemical properties of the alkanes. See, alkanes, as I said just now, alkanes, they contain only carbon, hydrogen, or carbon-carbon single bond. And it's very difficult to break this single bond. Therefore, whatever the reactions exhibited by these alkanes, they are all high temperature reactions, reactions which are difficult to carry out, reactions which occur only under drastic reaction conditions. So one such example is halogenation. So alkanes can be halogenated only in the presence of sunlight, that too at higher temperature, because this halogenation, it proceeds through free radical mechanism. It is a free radical substitution reaction, and therefore you all know free radical is a chemical species, highly reactive chemical species with very high energy, and it is highly reactive. It will be having very high energy. Therefore, once the free radical is formed, then that type of free radical can very easily attack carbon hydrogen bond and can break the carbon hydrogen bond and convert the methane into chloromethane, and successive halogenation, it results in dichloromethane, trichloromethane, and tetrachloromethane. And here the reactivity of tertiary hydrocarbon is higher compared to the secondary, and which is higher compared to the primary, because because here the tertiary hydrocarbon, the breaking of carbon hydrogen bond is bit easier. It is bit easier because after breaking of the carbon hydrogen bond, whatever the carbocation we get there, that carbocation stability is higher in case of tertiary hydrocarbon compared to the secondary and primary hydrocarbon. Therefore, easier the breaking of carbon hydrogen bond, easier will be the halogenation. But since breaking of the carbon hydrogen bond itself is difficult, halogenation can occur only through free radical substitution reaction. The simple addition of halogen in the presence of, in the absence of sunlight or at lower temperature is not possible here. Similarly, another reaction exhibited by alkanes, it is combustion. See, alkanes can be burnt at higher temperature, and on burning, they result in the formation of carbon dioxide and H2O. Even this burning, see, ignition temperature of hydrocarbons, because they are non-polar in nature, they are highly volatile, ignition temperature is very, very less. Therefore, these compounds can be ignited very easily. Once these compounds are ignited, once the combustion process is initiated, they undergo combustion, complete combustion, resulting in the formation of carbon dioxide and H2O. Again, this reaction is highly exothermic reaction, and also this reaction, it takes place at very high temperature. Combustion temperature will be very, very high. And this combustion reaction we use everywhere. This reaction is the basis for almost all the energy resources what we are using today. About 95% of the energy resources what we are using today, they are based on carbon containing fuels only. And wherever we are using carbon containing fuels, in majority of the cases, whether it is burning of coal in thermal power plant, or burning of petrol in petrol engine, or burning of diesel in diesel engine, or burning of furnace oil in the industries for the heating purpose, everywhere, the burning is because of the exothermic nature of this particular reaction. On combustion of hydrocarbons, we get carbon dioxide and H2O, and large amount of heat energy is liberated. And this heat energy is utilized in different format for production of electric current, for running of a two-wheeler, for running of a four-wheeler, and for eating purpose in the industries. Everywhere we use this particular property, this particular chemical reactions of alkanes. And alkanes, they can be subjected to controlled oxidation. Controlled oxidation in the presence of copper at 523 Kelvin, methane, it is converted to methanol. And in the presence of molybdenum oxide, heating at high temperature, methane, it results in the formation of formaldehyde. And ethane, it gives acetic acid in the presence of manganese acetate. And here also you can see this particular reaction is also, it also occurs at very high temperature and very high pressure, and along with the presence of a catalyst, because the oxidation reaction, it involves breaking of the carbon nitrogen bond in the hydrocarbon here, and this reaction occurs with difficulty under drastic conditions, that is at high temperature, high pressure, and in the presence of a catalyst. This is another example for controlled oxidation. The potassium permanganate, it oxidizes tertiary hydrocarbon, and here when the oxidation occurs here, the carbon nitrogen bond, the hydrogen which is attached to tertiary carbon atom, it is easily converted, it is easily broken, and it is converted to carbon hydroxyl group. And this is because of the positive inductive effect. The three methyl groups which are attached to this tertiary carbon atom, they provide the electron density. They are the electron donating groups, and electron density is provided. Therefore, whatever the carbocation is formed over here on breaking of carbon nitrogen bond, that carbocation is highly stable, and because of this, this particular carbon hydrogen bond can be easily oxidized. Therefore, even though alkanes are relatively non-reactive, the reactivity is very, very low. At high temperature, where the breaking of carbon-nitrogen bond or breaking of carbon-carbon bond is possible, only that type of reactions these alkanes undergo. Another reaction, another example is another high temperature reaction exhibited by alkanes is isomerization reaction. You all know isomer is an organic compound having same molecular formula but different structural formula. You can see here 2-methyl pentane and 3-methyl pentane are the isomers of N-hexane, where the molecular formula is same but the structure is different. And alkanes undergo this isomerization reaction. Linear aliphatic hydrocarbons can be converted into branched hydrocarbons. And this reaction occurs in the presence of aluminum trichloride catalyst and in the presence of HCl. And it is a Lewis acid. This Lewis acid, it breaks carbon hydrogen bond, resulting in the formation of carbocation. Again, you can observe here, this reaction is also high temperature reaction. It also occurs under drastic condition. In the presence of anhydrous aluminum chloride HCl, at a high temperature, it results in carbocation formation, and that carbocation, it results in the formation of these branched hydrocarbons, isomers of the linear aliphatic hydrocarbons. And another example for the high temperature reaction of alkanes is aromatization reaction, where the conversion is the conversion of the linear aliphatic hydrocarbon into cyclic aliphatic hydrocarbon, which on dehydrogenation results in the aromatic hydrocarbon. And conversion of this linear aliphatic hydrocarbons into aromatic hydrocarbon, we call it as aromatization. And aromatization reaction also occurs at very high temperature and very high pressure in the presence of appropriate catalyst. Vanadium oxide, chromium oxide, or molybdenum oxide are used as catalyst. And reduction reaction is carried out by using platinum as the catalyst at very high temperature of 773 Kelvin temperature. Another reaction exhibited by alkanes is, again, it is also high temperature reaction where the carbon-carbon bond, single bond is broken. And this reaction we call it as cracking. See, cracking, isomerization reaction, aromatization reaction, all these three reactions are used in the petrochemical industries. These three reactions are mainly used to increase the quantity of the petrol in the crude oil and also to increase the quality of the petrol in the petrol sample. Mainly the reforming reactions, isomerization reaction, aromatization reactions are used to increase the quality of the petrol, whereas cracking reaction is used to increase the quantity of the petrol. So all these reactions in the petrochemical industries, they are carried out at very high temperature, temperature of, you can see the temperature of more than 700 Kelvin here, and in the presence of the appropriate catalyst. For cracking, nowadays we use the Y type of zeolite as the catalyst. And here the cracking involves breaking of the carbon-carbon bond. Carbon-carbon covalent bond. Carbon-carbon covalent bond energy is very, very high and breaking is very, very difficult. Therefore, only in the presence of appropriate acid catalyst, whether Lewis acid or the Bronsted acid catalyst, and that to high temperature, high pressure, we can carry out these particular reactions. Another reaction exhibited is the steam reforming. Passing of the steam at very high temperature over the methane gas in the presence of nickel as catalyst. It results in the formation of a mixture of carbon monoxide and hydrogen. This particular mixture we call it as synthetic gas. And synthetic gas, it can be used as a reactant to obtain varieties of other hydrocarbon molecules through the Fischer-Tropsch synthesis. And this particular reaction, this reaction also occurs at very high temperature in the presence of nickel catalyst. Therefore, if you slightly observe the reactions exhibited by alkanes, see, alkanes are relatively inert molecules. They show very less chemical reactivity, and even though they show very less chemical reactivity, the reactions which are shown by these alkanes, they are all high temperature reactions, because the reactions here, they require the breaking of carbon hydrogen bond or carbon carbon bond. Therefore, if you study the reactions exhibited by alkanes, keeping this particular point in mind, where the breaking of carbon carbon bond is difficult, breaking of the carbon hydrogen single bond is also difficult. Therefore, all the reactions exhibited by alkanes are high temperature reactions, which can be carried out only at high temperature, high pressure, in the presence of appropriate catalyst. Whether it is halogenation, whether it is aromatization, whether it is steam reforming, whether it is isomerization reaction, all these reactions, oxidation of alkanes, cracking, and combustion, all these reactions are high temperature reactions. Now, let us discuss the structural features of alkenes, the second hydrocarbon, and how these structural features of alkenes, they influence their chemical properties. They influence how the structural features of alkenes influence their chemical reactivity. Now, the structure of a simple alkene, the first member of the alkene series, ethene, is given here. Ethene is CH2 double bond CH2. Therefore, looking at the structure itself, you can say here, the main difference between alkane and alkene is, in the alkene there is a carbon-carbon double bond. And in the carbon-carbon double bond, there are two bonds here. You all know, one of the bond is the sigma bond, which is formed by direct overlapping of the p orbital of the two carbon atoms. And another bond is the pi bond. And pi bond, you all know, it is formed by the side wave overlapping of p orbitals of two carbon atoms. Therefore, the carbon here, it is sp2 hybridized. Carbon in alkene, where the carbon is involved in the carbon-carbon double bond, that particular carbon atom is sp2 hybridized. And you all know, in the sp2 hybridization, the bond angle is 120 degree. And here, two carbon atoms, they are bonded together by means of one sigma bond and one pi bond. And this pi bond is completely different from the sigma bond. The bond energy of the pi bond is lesser than the bond energy of the sigma bond. Okay, therefore this lower bond energy of the pi bond in alkene is mainly responsible for almost all the chemical reactions which are shown by these alkene molecules. Therefore, the main difference between alkane and alkene is in the alkene there is a carbon-carbon double bond where there is a pi bond where the electron density available is very high, and also the bond energy of the pi bond is very, very less. Therefore, you have to keep these things in mind before you go through the chemical reactions of the alkene, so that you can very easily understand and very easily compare the reactions exhibited by alkanes with respect to that of reactions exhibited by the alkenes. Now let us see the properties of the alkenes and alkenes, and we shall compare those properties with the alkenes. The physical properties, boiling point, melting point, solubility of the alkenes, it's very similar to alkenes. But only difference is the variation in the physical property is also very, very similar. The only difference is here in alkene, because of the presence of carbon-carbon double bond, the polarity is slightly higher. When the polarity is higher, the intermolecular force of attraction is higher, and therefore the property like boiling point, melting point, it is higher in case of alkenes compared to the corresponding alkane. But with the gradation in properties, with the variation in the number of carbon atoms, it is almost similar when compared to the alkane. Therefore, the variation, whatever the difference in physical property we observe here, it is because of the more polarity of the alkene compared to the alkane, and that more polarity is mainly because of the presence of carbon-carbon double bond, that is the pi bond in the carbon-carbon double bond, and the hybridization of the hydrocarbon present, which is involved in the carbon-carbon double bond. That is, the carbon here is sp2 hybridized, whereas the carbon in the alkane is sp3 hybridized. Therefore, the set of chemical reactions exhibited by the alkenes is completely different when compared to alkanes. And here the carbon electron present in the pi bond, it is the main reason for the difference in chemical properties what we observe in case of alkenes. Let us see the properties, chemical properties of exhibited by these alkenes. The first one is alkenes, they undergo very easily the electrophilic addition reaction. See, electrophilic addition is addition of electrophile. See, electrophile is a chemical species which is attracted by the electrons. And in alkenes, there is a carbon-carbon double bond. There is a pi bond where the electron density is present in the sideway overlapped p orbitals, and that electron density is easily accessible for the electrophiles. Therefore, electrophilic reagents, they can be added across carbon-carbon double bond, and this particular reaction we call it as electrophilic addition reaction. Electrophilic addition reaction, addition of electrophile across carbon-carbon double bond, where the carbon-carbon double bond is broken and electrophile is added to the carbon-carbon double bond. One example is addition of hydrogen. Addition of hydrogen across the carbon-carbon double bond in the presence of nickel palladium catalyst, it results in the formation of the more stable alkane. Another example is addition of halogens. See, halogens, for example, if you take chlorine, chlorine is broken and it results in the formation of electrophile, and that electrophile can be added across the carbon-carbon double bond, resulting in the formation of 1,2-dibromoethane. Another reaction is another example for the electrophilic addition reaction exhibited by the alkenes is addition of hydrogen halides. Hydrogen halides addition, it goes according to Markovnikov's rule. See, Markovnikov's rule says when the when HCl is added across the carbon-carbon double bond, the negative part of the reagent, it is added to carbon atom containing less number of hydrogen atoms. Less number of hydrogen atoms. This is because the carbon containing less number of hydrogen atoms, it is, you can see here, it is attached to methyl group, and methyl group, it exhibits plus I inductive effect, and therefore the electromeric effect takes place here, and electromeric effect takes place from carbon number 2 to carbon number 1, and therefore carbon number 2 is positively charged. Therefore the negative group of the reagent, for example, if you are taking HBr, the negative group is Br minus. Br minus is added to carbon atom which is positively charged, and the positively charged carbon atom is the carbon atom which contains less number of hydrogen atoms. Therefore, this rule, it is defined as the Markovnikov's rule, which says the negative end of the negative part of the reagent is added to the carbon atom which contains less number of hydrogen atoms, and positive part is added to the carbon atom which contains more number of hydrogen atoms. Therefore, on addition of HBr to propene, we get 2-bromopropane as a major product and 1-bromopropane as a minor product, and this is mainly because the addition takes place according to Markovnikov's rule. And addition is against Markovnikov rule, that is, we call it as anti-Markovnikov addition. And when the addition is carried out in the presence of dibenzoyl peroxide and in the presence of sunlight, because in this type of reaction, it is not electrophilic addition reaction. It is instead, it is the free radical substitution reaction. And therefore, whatever the free radical is formed over here, that free radical attacks the carbon atom in such a way that the resulting free radical should be more stable. And here there are two possibilities here. The free radical, whatever the free radical is formed, it can be a primary free radical, or it can be a free radical present on the primary carbon atom, or it can be a free radical present on the secondary carbon atom. Now, secondary free radical, it is more stable when compared to the primary free radical. Therefore, a secondary free radical is formed at faster rate when compared to the primary free radical. Therefore, addition of HBr to the unsaturated hydrocarbon alkene, it goes against the Markovnikov's rule, and we call it as anti-Markovnikov's addition, where the where this 1-bromopropane formed over here, it is the major product, which is because of the most stable free radical when compared to the 2-bromopropane formed over here. Therefore, the addition takes place by different mechanism. Even though addition is same, HBr is added to the carbon-carbon double bond here. Under normal condition, the addition takes place according to Markovnikov's rule, whereas under in the presence of a peroxide and in the presence of sunlight, where the addition takes place through free radical mechanism, there the product what we get is opposite to the Markovnikov addition. Another example for the electrophilic addition reaction of alkenes is addition of sulfuric acid, where H is added to one carbon atom and HSO4 minus is added to another carbon atom. Therefore, those are the examples for the electrophilic addition reactions exhibited by alkenes. And alkenes, they undergo oxidation. They undergo oxidation more easily when compared to the alkanes, because in the alkanes it's difficult to break carbon-hydrogen bond, difficult to break carbon-carbon bond, whereas in alkene they can be subjected to oxidation without breaking of the carbon-hydrogen bond, just by breaking of the carbon-carbon pi bond, because of the electrons which are there in the pi bond, they are loosely bound to both the carbon atoms, and therefore alkenes can be oxidized very easily when compared to the alkanes. And one example is the Bayes reagent, addition of when the alkenes are treated with KMnO4, it decolorizes the color of the KMnO4. That is because of the formation of ethylene glycol. Ethylene glycol and here the pink color is discharged, and black brown PPT of MnO2 is formed. And this is the test for the presence of carbon-carbon double bond. And this reaction is exhibited by only alkenes where there is a carbon-carbon double bond. But same KMnO4, when it is added to alkanes, the reaction, they will not undergo reaction in the presence of cold alkaline KMnO4. There is no reaction of alkanes, whereas alkenes undergo reaction readily. Another reaction exhibited by alkenes is addition of ozone, ozonolysis. It results in the formation of ozonide, which on hydrolysis, it results in the formation of the formaldehyde. Ethene, it results in the formation of formaldehyde. Similarly, other hydrocarbons, other alkenes, higher alkenes, they result in the formation of aldehydes and ketones. And this is another example for the electrophilic addition reaction. Therefore, these chemical species can be added easily across the carbon-carbon double bond, and therefore alkenes, they exhibit the chemical reactivity mainly because of the presence of carbon-carbon double bond. Another reaction exhibited by alkenes is polymerization. Polymerization reaction, again, it is due to presence of carbon-carbon double bond here. And during polymerization, carbon-carbon double bond is broken and it results in the formation of the polymer. And therefore, the polymer where the carbon-carbon double bond is absent. Therefore, if you observe the reactions exhibited by alkenes, almost all the reactions exhibited by the alkenes are due to the pi bond which is there between carbon and carbon. And pi bond, the electron density, it is loosely held by both the carbon atoms. The bond energy of the pi bond is lesser than the sigma bond, which is easy to break, and therefore, the electron density is easily accessible for the reagents. Therefore, alkenes, one of the major reaction exhibited by the alkenes is electrophilic addition reaction. Electrophilic addition reaction, where the electrophile is added across the carbon-carbon double bond. And in addition to that, the other reactions which are due to that carbon-carbon double bond are exhibited by the alkenes. Now let us see the chemical structure of the alkyne. A simple alkyne is acetylene. In the acetylene, you can see the structure here. It is a linear hydrocarbon where the bond angle between carbon hydrogen and carbon carbon bond is 180 degree. And here the carbon is sp hybridized. And in the acetylene, you can see here, there is one carbon-carbon single sigma bond, and there are two carbon-carbon pi bonds here. And pi bonds are formed by the sideway overlapping. You can see the structural features of acetylene here. So acetylene, the bond distance between carbon and carbon is lesser compared to alkene and alkane. And the distribution of the pi electron density, it is more uniform here when compared to alkene. Therefore, the almost distribution of the pi electron density, it is in the cylindrical manner. And this pi electron density, it is closely bound to the carbon atoms when compared to the alkene. Therefore, the pi electron density of the alkyne, it is not easily accessible to the reagents as easily as in case of alkenes. Therefore, accessibility is more difficult here. And this difference in structural features. And another main difference is here, carbon atom is sp hybridized. And in the sp hybridized carbon atom, the contribution of the s character is 50% and p character is 50%. And s character, s orbital, it is the round orbital, it is almost near to the nucleus of the carbon. Therefore, higher the s character, more is the bounding of the electron density to the nucleus of the carbon atom. Therefore, the electron density in the bond, it is tightly held together. It is attracted by the carbon. The carbon which is involved in carbon-carbon triple bond in the alkyne, it is more electronegative. Therefore, electron density is more towards the carbon. Therefore, the carbon hydrogen bond, it has very lesser bond energy. And the electron density of the carbon-hydrogen bond, it is attracted by the carbon here. And therefore, in alkynes, this carbon-hydrogen bond can be easily broken. In fact, the carbon-hydrogen bond, it exhibits high polarity and it is acidic in nature, and the proton can be separated very easily from the carbon-hydrogen bond. Therefore, whatever the difference in properties of the alkynes we observe here, it is mainly because of the structural features what we observe here. Let us see those properties one by one. So again, here the physical properties, boiling point, melting point, they are a bit higher in case of alkynes when compared to alkenes and alkanes, because polarity in alkynes is higher when compared to alkenes and alkanes. And similar to alkynes, they also exhibit electrophilic addition reaction. They undergo electrophilic addition reaction like addition of hydrogen, addition of halogens, addition of halogen acids, addition of water. All these reactions, what we observe in case of alkenes, they are also shown by the alkynes also. But the accessibility of the electron density, the pi electron density for the electrophilic reagents, it is lesser in case of alkynes when compared to the alkenes. Therefore, alkanes undergo electrophilic addition reactions with much more difficulty when compared to the alkenes. Therefore, even though they exhibit the similar properties, those properties these chemical reactions they occur under more drastic conditions. They require more energy when compared to when compared to these reactions what we observed in case of the alkenes. And in addition to that, alkynes they exhibit the acidity and they undergo cyclic polymerization, which are not shown in case of alkenes. These are the examples of the chemical reactions exhibited by alkynes. Alkynes say hydrogen can be added across the carbon-carbon double bond, carbon-carbon triple bond here, and successive addition of hydrogen, it results in the formation of alkene and then alkane. And addition of hydrogen, it is as good as in case of alkene. The reactivity of alkenes and alkynes both are very similar. But in case of addition of the halogen, the reaction takes place more easily in case of alkenes when compared to the alkynes. So addition of water to alkynes, it results in the formation of alcohols. Alcohols and tautomerism, they result in the formation of aldehydes and ketones. This is one example for the electrophilic addition reaction of alkynes. The specific reaction what we observe in case of alkynes, which is not observed in case of alkenes, is the acidic nature of the carbon-hydrogen bond, which is present in the alkynes. Carbon-hydrogen bond, the carbon is a carbon which is involved in carbon-carbon triple bond in alkyne. It is sp hybridized, and it has 50% of S character. Therefore, it is electronegative, and the electron density in the carbon hydrogen, it is attracted by the carbon. Therefore, this carbon hydrogen bond can be easily broken. For example, when it is subjected to reaction with sodium, the hydrogen can be removed from the carbon hydrogen bond, and there is evolution of hydrogen. This reaction is very similar to the reaction what we observe in case of inorganic acid like dilute HCl. Same type of reaction is exhibited by alkynes. This acidity of the carbon hydrogen bond of the carbon atom which is involved in the carbon-carbon triple bond. This is the special type of reaction what we observe in case of alkynes, and this reaction is mainly due to the structural feature of the alkyne. Another the special reaction observed in case of alkyne is alkyne at very high temperature in the presence of red hot iron or copper tube, which is used as a catalyst. It undergoes cyclic polymerization reaction, resulting in the formation of the most stable hydrocarbon, that is benzene. These are the few properties, chemical properties, which are exhibited by alkynes. You can see the alkynes, the properties are similar to alkenes, but whatever the difference we observe here, it is mainly because of the nature of the hybridization of the carbon atom involved in the carbon triple bond. That is, here it is sp hybridized, and in alkene it is sp2 hybridized. And because of that and nature of the electron density, nature of the pi bond, the chemical reactivity of alkyne is slightly different when compared to the alkene. Now let us discuss about the chemical reactivity of aromatic hydrocarbons. One common example, the basic example for the aromatic hydrocarbon is benzene. You all know in the benzene there are 3 carbon-carbon double bonds. Therefore, carbon-carbon double bond, it looks very similar to the carbon-carbon double bond of alkene. Here also the carbon is sp2 hybridized. There is a carbon-carbon double bond. Each and every carbon is involved in the carbon-carbon double bond. But the properties of benzene, they are completely different when compared to the properties of the alkenes. And this is mainly because of the aromaticity. Aromaticity in benzene, it is mainly because of the extensive conjugation of carbon-carbon double bond. In benzene, you can see the carbon-carbon double bond which are present here, they are alternate carbon-carbon double bond. Therefore, the side wave overlapping of p orbital, it is extended across all the carbon atoms. Therefore, this electron density which is present, the pi electron density which is present in the carbon-carbon double bond, it is completely delocalized. It is delocalized among all the 6 carbon atoms which are there in the benzene ring. And therefore, here all pi bonds, they are completely delocalized. And the pi electrons which are there in carbon-carbon double bond, they do not belong to the single carbon atom or 2 carbon atoms, as we observe in case of alkene. So in case of alkene, whatever the pi electron is there, in case of alkene as well as in case of alkyne, whatever the pi electrons are there, they are present in between those 2 carbon atoms. Therefore, they are accessible to the chemical reagents across those 2 carbon atoms. But here, the electron density is completely delocalized. It belongs to all 6 carbon atoms, all 6 carbon atoms. And this delocalization of pi electrons, it brings in more stability into the benzene ring. And therefore, benzene is aromatic in nature. This particular property, delocalization of electrons, we call it as aromaticity. And this structural feature, the difference in structural feature of benzene, it is mainly related to whatever the chemical properties, what we observe in case of benzene. Therefore, aromatic hydrocarbons, they exhibit different chemical reactions, different set of chemical reactions than the alkene and alkyne. Even though here also there is a carbon-carbon double bond, and which is a pi bond, and even though carbon is sp2 hybridized, and everything which it looks very similar to the alkene, but because of the delocalization of the pi electron system, because of the that particular the planar nature of the benzene, aromaticity of the benzene, the chemical properties exhibited by aromatic hydrocarbon like benzene, it is completely different when compared to alkene and alkyne. Let us see the chemical reactions, what chemical reactions are exhibited by these aromatic hydrocarbons. They mainly exhibit the aromatic hydrocarbons. They exhibit electrophilic addition reactions. Addition reactions similar to alkenes. Similar to alkenes, but these addition reactions, they do not occur very easily as in case of alkene, because the pi electron density in alkene, it is easily accessible by the chemical reagents, and electrophiles can easily attack the electron density between carbon-carbon double bond, where that possibility is lesser in case of aromatic hydrocarbon because of delocalization of the pi electrons. Therefore, even though they exhibit electrophilic addition reactions, they exhibit electrophilic addition reactions with more difficulty when compared to the alkenes. And but this Aromatic hydrocarbons, they exhibit electrophilic substitution reactions. Electrophilic substitution reaction because you will see when electrophilic substitution reaction occurs, there is stabilization of the aromatic ring there. These are the examples for the addition reactions. Addition of hydrogen. When hydrogen is added across to the benzene in the presence of nickel catalyst, you can see there this reaction occurs at higher temperature. It results in the formation of saturated hydrocarbon, cyclohexane, but reaction occurs at higher temperature by using a nickel as a catalyst. Okay, therefore reaction is feasible only at higher temperature and that in the presence of catalyst. In the absence of catalyst at lower temperature, addition reaction is not possible because addition reaction here it involves the removal of the aromaticity of the benzene ring, where the benzene ring is moving from the aromatic ring to normal cyclic hydrocarbon. And chlorine can be added through the free radical substitution reaction in the presence of sunlight, and this substitution reaction it occurs through free radical mechanism. The free radical it is of very high energy and it can easily break the carbon hydrogen bond, and it can result in the formation of chlorinated benzene, and we get benzene hexachloride by addition of 3 molecules of chlorine to the benzene. And similar to alkenes, we can add ozone across the carbon-carbon double bond of the benzene, and 3 molecules of ozone can be added, resulting in the formation of glyoxal. But the reaction possibility of the addition of ozone to benzene is more difficult when compared to the addition of ozone to normal carbon-carbon double bond, as in case of alkene or alkyne. The characteristics reactions shown by the aromatic hydrocarbons are the electrophilic substitution reactions, where electrophile can be substituted for the hydrogen atom present in the benzene ring. And here, the addition of electrophile to the benzene ring, which is rich in pi electrons, it is the rate determining step, slow step, and it results in the formation of rhenium ion. And rhenium ion, it involves the next step after addition is the stabilization of the rhenium ion here. And rhenium ion is stable, it is stabilized, and due to resonance stabilization of the rhenium ion, then this benzene ring it undergoes electrophilic substitution reaction very easily. And after the stabilization, the last step is the first step, where the hydrogen is removed and electrophile is finally added to the benzene ring. Examples for the electrophilic substitution reactions are: one is the nitration, which takes place in the presence of nitric acid, sulfuric acid at around 313 to 333 Kelvin. And you can see here in the nitration, NO2 plus is the electrophile. NO2 plus is the electrophile. It attacks this carbon atom, and finally it results in the breaking of carbon hydrogen bond, and we get the nitrobenzene. Another example is chlorination. Chlorination in the presence of aluminum trichloride, it results in Cl plus as electrophile, and that Cl plus attacks the carbon atom. It results in the formation of the chlorobenzene. This is another example for the electrophilic substitution reaction exhibited by benzene ring. And this is another example for the electrophilic substitution reaction, bromination, where Br plus is the electrophile. And one more example is sulfonation. And two more typical examples are Friedel-Crafts alkylation reaction, where we use same Lewis acid aluminum trichloride in the presence of an alkyl halide. It results in the formation of the alkyl cation, carbocation, which attacks the carbon atom, resulting in the formation of toluene. And another example, the final example is Friedel-Crafts acylation. You can see in all these reactions, all these reactions, they belong to the category of electrophilic substitution reaction. Therefore, one of the major characteristic reaction of aromatic hydrocarbons is the electrophilic substitution reaction. Electrophilic substitution reaction, where electrophile attacks the benzene ring, and which is the intermediate is resonance stabilized. Therefore, whatever the product formed is whatever the electrophilic substitution product, whatever we get, it is the stable product. Therefore, thus we have seen the comparison between the structure of major four hydrocarbons: alkanes, alkenes, alkynes, and aromatic hydrocarbons. And what is the main difference in structure between one type of compound to other type of compound? How this difference in structure, it is clearly related to the difference in reactivity. To recall briefly, here you can see the alkanes are relatively non-reactive. That is mainly because the nature of the bonding present in the alkane is only a purely covalent bond, carbon-hydrogen bond, carbon single bond, which is of very high energy, which is very difficult to break. Whereas in alkene, whatever the reactivity exhibited by the alkene, it is because of the presence of this pi bond, because of the side wave overlapping of the p orbitals between two carbon atoms. And whatever the properties we observe in case of alkynes, it is because of the sp hybridized carbon atom and the cylindrical distribution of the electron density across the carbon-carbon double bond. Whereas in aromatic hydrocarbon, whatever the properties which are shown by the aromatic hydrocarbons, it is because of the aromaticity, because of the resonance stabilization. Therefore, even though all these four compounds, they are made of carbon and hydrogen only, and in these three compounds, even though there is a carbon-carbon double bond, and even though hybridization of the carbon atom in alkene is similar to aromatic hydrocarbon, even there are similarities, but the chemical properties exhibited by each and every class of the compound is different. And this difference is mainly because of the difference in structure, difference in the nature of the bonding, nature of the hybridization which is involved in these molecules. Okay, with this, I will conclude my talk. If you are having any doubts, you can you can ask your doubts and you can clarify your doubts. Thank you.
Thank you, Chandra.
Thank you.
So,
Thank you, Silagoda sir, and thank you for giving me the opportunity for giving this talk in the KSTA webinar series. And I look forward for your cooperation in future also for sharing our knowledge to the student community. Thank you.
thank you, Chandra. It's an immense pleasure to thank you once again. So, dear students, please ask any questions or doubts. ಚಂದ್ರ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಹಾಕಿಲ್ಲ ಯಾವ್ದೋ ಕ್ವಶನ್ಸ್
ಹೌದಾ?
ಯಾರು ಕಳಿಸಿದ್ರೆ ಸೆಂಡ್ ಲೇಟರ್ ಆನ್ ಯುವರ್
ಓಕೆ. ಇಫ್ ಏನಾದ್ರು ಕ್ವಶನ್ಸ್ ಇದ್ರೆ ಫಾರ್ವರ್ಡ್ ಮಾಡಿ, ವಿಲ್ ಆನ್ಸರ್.
ಸೊ ಥ್ಯಾಂಕ್ ಯು ಚಂದ್ರು. ತಾವು ಇವತ್ತು ಹೈಡ್ರೋಕಾರ್ಬನ್ಸ್ ವಿಷಯದ ಮೇಲೆ ತಾವು ಕೊಟ್ಟಂತ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವು ಒಳ್ಳೊಳ್ಳೆ ಉದಾಹರಣೆಗಳ ಮೂಲಕ ಹೈಡ್ರೋಕಾರ್ಬನ್ಸ್ ಬಗ್ಗೆ ಹಲವಾರು ಮಾಹಿತಿಗಳನ್ನ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೀರಾ. ಸೊ ನನ್ನ ವೈಯಕ್ತಿಕವಾಗಿ ಹಾಗೂ ನಮ್ಮ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿಯ ಪರವಾಗಿ ತಮಗೆ ಧನ್ಯವಾದಗಳು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು.
ಸೊ ಅದೇ ರೀತಿ ನಮ್ಮ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಅಧ್ಯಕ್ಷರಾದಂತ ಡಾಕ್ಟರ್ ಅಯ್ಯಪ್ಪನ್ ಸರ್ ಅವರು ಕೂಡ ಆಗಮಿಸಿರ್ತಕ್ಕಂಥ ಅಯ್ಯಪ್ಪನ್ ಸರ್ಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು ಹೇಳ್ತಾ, ಹಾಗೂ ನಮ್ಮ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು ಹೇಳ್ತಾ, ಸೇರಿದ ಎಲ್ಲ ನನ್ನ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರು, ಸಹೋದ್ಯೋಗಿಗಳು, ವೆಬೆಕ್ಸ್ ವೃಂದದವರು ಹಾಗೂ ನನ್ನ ಅಧ್ಯಾಪಕರೇತರ ಎಲ್ಲರಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಒನ್ಸ್ ಅಗೇನ್ ಥ್ಯಾಂಕ್ ಯು ಮೃಣಾಲ್. ಥ್ಯಾಂಕ್ ಯು ಚಂದ್ರು.
ಥ್ಯಾಂಕ್ ಯು.
ನಾನು ಸಾಯಂಕಾಲ ಫೋನ್ ಮಾತಾಡ್ತೀನಿ ನಿಮ್ ಜೊತೆ.
ಓಕೆ.
ಓಕೆ ಥ್ಯಾಂಕ್ ಯು.
ಓಕೆ.